Everything at YG starts here. Every day we get aluminium stock, which are these huge sheets delivered. They come in a wide variety of thicknesses, from very thin material like this through to very thick 75mm material, which is what we use for our Titan. These sheets are then processed in two ways. Over there we have our Portatec vacuum table mill, and that was the old way we used to process things. I'm going to walk you through the new process. We've been using this process for the last two and a half years, and it's about 20 times faster and more precise, and it also minimizes material wastage. Over here we have the water jet. This water jet is a very large surface, latest generation water jet cutter. It uses extremely high pressure water with an abradant, which is a gemstone garnet, which is injected into the water stream, and it can cut aluminium up to 150mm thickness. You can see the cutting head over there, and we have some videos that will let you see how it cuts the aluminium. What this generates is blanks. You can see some of the blanks here on the table, but I'll walk you around and I'll show you what we do with those blanks in the next step of our production. These four machines are the cornerstone of our production. They're four of the latest generation, highest spec DMG Mori 3-axis CNC machines. They have a very large working area and they're extremely precise. We have every option possible to ensure that that precision is there and that it's constant. They're double temperature corrected. They have every capability to make sure that they can cut to within 0.001mm accuracy. What we do is we take the water jet blank, which is what you saw the water jet cutting next door, and we mount it onto a jig that then goes in one of these machines. The first step we call side one. In side one, the interior face of the particular part is cut. So you see here, this is a Sonia 3.1 face. This is the blank from the water jet. This is side one, and you see all the interior detail has been cut. Once this is complete, we flip it around and we cut the finished face. We call this side two. If I turn this over, you can see all the cutting that's in the side one is on the back of this, and then it's flipped around in the machine and this surface is cut. There's a huge amount of time that's invested in this process. Cutting this side one can be a couple of hours. Cutting this side two can be 6 hours. And that's for a relatively small piece like this Sonia 3.1 face. This is how we ensure the precision that enables us to use simulation to come up with such acoustically optimized loudspeakers. For example, this tweeter surround, the Stellar surround in our version 3 models, has to be cut to an accuracy of 0.005mm for it to be effective. The accuracy we have here enables us to have that acoustic performance delivered, and we can make sure it's delivered in every single speaker we produce. The four machines here ensure that we can continue with production even if one of the machines has a fault. All four of them are identical, and all four of them have exactly the same sets of tools. These tools are the things which actually cut the aluminium, and I can show a few of them to you here, and my colleague Jason can show some of them in the machine as well. Inside here, you can barely see it, but there's a magazine that has a whole set of tools available all the time for this machine. On the tray are supplemental tools that are used more rarely, and we load when we need them for particular jobs. We use a lot of custom tools. So for example, if you've seen a Peaks loudspeaker, the two edges of the face are cut by this tool. So it cuts in this direction, and you'll see that curve. That's exactly the shape of the two edges of a Peaks loudspeaker. We then have this. This is a lens bit. This is designed exactly for us. Coolant comes through it to make sure that it cuts as cleanly as possible. And you can see it has a very gentle curve to the top surface. This is perfectly designed to cut the smooth surface of Peaks loudspeakers. If you come around here, we can show you some of the other tools that we use and what they do specifically. For example, if you see in the Sonya 3.1 face, there's a hole for the tweeter. We have a specific tool, which is a drill, which cuts that hole exactly in a single pass. We're just swapping ground to it now. And if you look here, you have that, which is a single drill, and it's exactly the size of the hole that we cut for the tweeter. So this is partway through a program. We paused it so you can see all the bits that have been cut off. And we're about to do the next step in the program. Shall I close it? Actually cutting apart. Okay, and then we can go across to the crossovers, unless you wanted more of this. for example, we have specialist tools for cutting flat areas. I can swap across to one of those. Wow. That cuts large flat surfaces very accurately and very quickly. And each one of these, coolant comes through to force all of the chips away. So while it's operating, you can see that jets through and that cleans the chips away immediately, making sure that the cut is very clean and precise. I talked a little bit about the jigs, and maybe that's the next thing that's worth taking a look at. We've paused this so as to reduce the noise. So this is partway through running a program. You'll see that there are two pieces here. These are mounted to a jig. The jig enables us to place the pieces very accurately inside the machine. And when we swap from side 1 to side 2, it ensures that the registration between the two sides is very accurate. We have a jig for every side of every part. And for some parts, which we produce a lot of, we have multiple jigs so that we can run several machines at the same time producing the same part. So that's a brief overview of machining. This process that we use for parts is exactly the same process that we use for making our cones at the moment. So if you come over here, I'll show you the cones. Each one of our cones starts off as a blank, just like the parts that I showed you there. This is the blank for an 18 centimeter cone, which is the mid-range driver that you find in the Haley, the Vantage, in the Ascent, in the Talus, in the Summit, in so many of our speakers. This is the blank. We then cut it side 1. So you can see this side is still flat, and we cut the back surface of the cone. Inside this are all the reinforcements that strengthen the cone. We then take this side 1 and we cut it side 2 to produce the finished cone. So you can see if I turn this over, all the detail which is in side 1 becomes the reverse side of side 2. We start off with a blank which is several kilograms, and we reduce it to a final cone which is just a few grams. This cone is so strong, despite the fact that it's only a few grams, that if I put this down on the ground, I could stand on it without damaging it. These cones ensure the performance of our speakers, and they're used in every model. Even from our entry model, the Cairn, we have these same milled cones, and the same cones go through to the drivers which are in our flagship products. We're always trying to find ways to do things better, and I'm very excited about some progress we're making. This is a great way of making the best cones in the world. But you start off with 3 kilograms and you end up with a few grams. Even if we recycle every scrap, that's a lot of recycling, a lot of energy. We could do better. We've been working for the last 4 years on a way of producing these so that we start off with a sheet. And there are amazing new techniques such as roboforming, where 2 opposite hammers move to form the cone shape. These allow us to control the thickness and the stress patterns inside the cone, even when we're forming it from a single sheet. And we believe we're very close to having a process which works from a sheet, which delivers the same performance as milling without having to have this process. Right now, this sheet-based process is a lot more expensive, but we're trying very hard to find a way to be able to use it in production because we think it's a much better way to go. Whichever errand. At YG, we're unusual in that we mill all of our own crossover PCBs and we do all of our own crossover assembly right here. The PCBs there are two forms. We use a multi-layer, very thick PCB board for reference. This is resonance damping. It has very special dielectric properties. It has an extra thick copper layer on it. We mill this away to form the tracks that we need. And this enables us to have the precision of tracks on there, which are guided by our simulation, to make sure that the tracks are interacting with the magnetic field in exactly the way that we want. So here's an example. This is a Sonia mid PCB, and these are the tracks that we mill on the back. This is all done in-house on the same machines that you saw producing the parts. So here are a few examples. This is a Haley. This side is the tweeter crossover for a Haley. You see here we have these custom aluminium alloy foil capacitors. These are made to our own design with a very special dielectric and a very special surface finish to the foil to give us exactly the properties that we need. These are our copper foil capacitors. These use a copper-silver alloy for the foil with a very special dielectric. These have incredible capabilities in terms of the final tiny bits of detail in treble. We use here metal foil resistors, lits, wax damped inductors, and very high quality components in every place. This side is the mid crossover, and this is just from a Haley or a Vantage. I showed you that board earlier. This is a Sonia 3 tweeter crossover. Again, you can see our copper alloy foil capacitors, our aluminium alloy foil capacitors, and the metal foil resistors. And on this side, that's the mid crossover. Again, we take a lot of care over these. So much of the performance of our loudspeakers comes from the crossover design and the capabilities we have with both the design and the components that we use. In our speakers, you'll find that the bass crossovers are often mounted in metal cages, like this. This is a Haley bass crossover, and underneath this go two large iron cord inductors that we use for the bass circuit. These metal sides actually play a really important acoustic role inside the cabinet because they break up standing waves. The difference of these holes and the pattern of holes is very audible when it comes to the acoustic performance of the bass cavity. Everything in this, again, is machined and assembled in-house. What you're seeing here is reference crossovers from our reference 3 range, but there's just as much care taken over the crossovers inside our Peaks loudspeakers. And in a moment I can take you across and show you some of the Peaks crossovers. We saw over there the reference 3 crossovers on the very thick black circuit boards. We may not be able to use that very expensive black circuit board for our Peaks, but in every other way they benefit from the same technologies and the same components. So here we have some examples of Peaks crossovers. This is from our entry-level model, the Cairn. You can see inside this we have the same Litz wax inductors and the same aluminium foil capacitors. These enable us to have incredible phase coherency between the different drive units. The design and the components ensure that. And in the same way, if you look at the track layouts, these are optimized using simulation so that they interact with the magnetic field of the inductors in exactly the way that we want. Taking a step up through the range, this is a Talus crossover. Here you have our own custom polypropylene caps. These have a very special 2-layer dielectric and very special behavior. And then the next step, this is an Ascent. As you can see, we take our crossovers very seriously. This is the heart of the technology inside our speakers and a very strong part of the differentiation of how they sound.